if someone says the word spin glass, what the first image that might come to your mind is some kind of complex, rugged energy or free energy landscape with many hills and valleys and with different configurations kind of associated with these different valleys. Okay? Now, actually deriving a landscape like this is a notoriously hard problem, even for very, very well-studied spin glasses. But the fact that you can have this type of landscape with stable minima at finite energy densities surrounded by barriers is most clearly established for spin glasses in kind of geometrically non-local or very high-dimensional models. Okay, so an example is the so-called Sherrington-Kirkpatrick model, which is an all-to-all Ising model with frustrated Ising interactions of either sign. Okay, and the point is that when I have this type of complex free energy landscape, I have many, many different local minima. And what makes this a glass is that these minima are associated with equilibrium states, and they have an asymptotically diverging lifetime below some glass transition temperature, which I'm going to call Tg. Okay, so in particular, this means if I start in some state in this well, and again, I start doing something like local Glauber dynamics, okay, I'm going to remain kind of in the vicinity of this state, trapped in this well for some diverging amount of time. Okay. As long as my dynamics are done according to some temperature, which I'm going to call Tg. Okay? Crucially, this is a dynamical memory transition, and in many cases, this need not be accompanied by any kind of thermodynamic non-analyticity in the partition function. Okay? So the partition function can remain completely analytic while you have this kind of dynamical memory transition. In addition, most of these minima, unlike the Ising model, in the Ising model I had two minima, which was mostly all up and mostly all down, and they were related by the global Ising symmetry, and that's why this was spontaneous symmetry breaking, okay, because you act with the symmetry to go from one equilibrium state to the other, and those equilibrium states break the symmetry. Here, I have most minima are not related by symmetry, so you shouldn't think of this as spontaneous symmetry breaking. And you have many, many more global minima than local minima. Okay, so even if you have many degenerate ground states, you might think that you have some complicated symmetry group which allows you to go from one ground state to another, but then you also have all of these additional states at finite energy density, which are both not related by symmetries and are nevertheless stable. Okay. So now I can use a combination of all of these minima to encode many different classical bits. Okay, so if I have 2 to the k stable minima, this allows me to encode k logical classical bits. And again, because of this landscape and this thermal stability, the system can now serve as a robust memory encoding these many classical bits distributed across all the different minima. Okay. So a question then is, can we encode quantum memory in a similar way? Okay, so classical spin glasses and classical spontaneous symmetry breaking order have been studied for several decades, but on the quantum side, our understanding of quantum memories has mainly just focused on kind of conventional quantum topological order. So the question is there an analog, a topological analog of this kind of spin glass phase? Okay, and the answer turns out to be yes. There is a new type of order that you can talk about, which we called topological quantum spin glass order. In order to encode quantum bits, I do need my states to be topological, which comes with which means they should be locally indistinguishable. They should have a large degree of quantum entanglement. Okay, so the type of phase that I'm going to be talking about is one which is going to be characterized. It's going to marry two notions. Okay, which are the two pieces of its name. It's going to have spin glass order first. So what you should think of when I say spin glass order is exponentially many stable minima and exponentially more stable minima with increasing temperature. Okay, so you have many different equilibrium Gibbs states. And then in addition, this can be thought of as a type of classical complexity of the free energy landscape that's coming from the spin glass part of the name. But then there's also the topological part of the name, which tells you that each minimum should host a Gibbs state with long-range entanglement. I'll tell you what that means. And the system, in this case, actually has many, many different embedded quantum memories within its landscape. Okay? And this is now a feature of quantum complexity, okay, because we're talking about this long-range entanglement of these associated Gibbs states. So, yeah.
Maybe it's just like terminology, but when you call the classical
yeah.
system robust, like, do you not care that the minimum move around when you add like a random longitudinal field?
Great. So I won't talk about that, but that's actually a very good question. And the point is that even though the minima move around, the Gibbs state that's associated in each minima is stable. So there's a kind of absolute stability in these models, in that you have a minima, it hosts a state, and you can add, because these barriers, so I'm going to spend a lot of time talking about barriers. If you add a weak perturbation, your barriers don't get destroyed, which means if you started with a Gibbs state in a well, that Gibbs state gets smoothly deformed as you change your Hamiltonian. And that's really why, you shouldn't think of this as coming from symmetry breaking, because you add these fields and you can take things that were ground states and promote them, but the Gibbs states will remain preserved and will smoothly continue. So it's really kind of like an emergent symmetry, if you will, or an absolute stability. Yeah. Okay, so we actually prove a theorem, and I want to say that even as far as the classical spin glass literature goes, known results that can be proved about classical spin glasses are actually very few and far between, despite decades of work. So these types of models with the types of techniques that have been used to prove properties about codes actually helped us prove various things about spin glasses that were quite elusive, even for classical spin glasses. Okay, so the theorem is that there are going to be sparse Hamiltonians which will realize all of these properties for t less than t glass. The first property is what's called shattering in the literature, which means that there are going to be exponentially many distinct Gibbs state components. I'm going to define for you precisely what I mean by a Gibbs state component, but you should think of this as an equilibrium state or a state that's going to asymptotically be an equilibrium state. It's going to have some lifetime that's diverging exponentially with n in some way. So there are going to be exponentially many distinct Gibbs state components, each with exponentially small weight and with a lifetime diverging as some stretched exponential of system size. Okay, that's what I mean by a Gibbs state component. But then, in addition to shattering, I also have this property called incongruence. This was a word that Fisher and Hughes invented in the context of spin glasses. And what this means is that the configurational entropy density, you can think of all of these Gibbs states as kind of, this quantifies some kind of complexity of the free energy landscape, and you want this to grow with temperature. So what this actually means is that most Gibbs states are not associated with ground states. Okay, they don't even locally look like ground states. So you have many, many more stable equilibrium states as you increase the temperature. Okay, so these two features, shattering and incongruence, is the classical aspect. And then the quantum aspect is that each or with high probability, each Gibbs state component is long-range entangled. And in fact, it's going to be an even stronger statement. I'm going to say not only is the Gibbs state long-range entangled, but the subspace of Hilbert space that the Gibbs state is associated with will contain no trivial short-range entangled states. Okay, so this is a much stronger form of topological order, even when compared to the 4D toric code, for instance, where even if the Gibbs state is long-range entangled in that case, states at low enough temperatures, there are many, many short-range entangled states. Okay, and finally, these models are going to form many emergent quantum memories. I use the word emergent because there's going to be quantum memory associated with the ground state manifold, but then you can actually use all of these excited state wells to also encode many, many more quantum memories. So there's going to be many embedded quantum memories within the same landscape, and the system actually preserves some combination of classical and quantum memory in a way that I'll make precise. Okay? Yeah.
Sorry, could you repeat why this point 3 isn't captured by the 4D toric code?
Yeah, so this is the stuff on NLTS that Nico worked on, right? So in the 4D toric code, so a long-range entangled Gibbs state, psi rho long-range entangled, is one that cannot be written as a convex combination of short-range entangled states, right? And the Gibbs state for the 4D toric code is certainly that. But now I'm making a stronger statement, which is that there's a subspace associated with the Gibbs state, and no state in that subspace is short-range entangled. So for instance, for the 4D toric code, just imagine tiling your system into boxes, okay? And within each box, you can put a toric code, okay? And by making these boxes large while still being order 1 in size, you can make the energy density arbitrarily low. So you have a state which is now below TC, but this is a short-range entangled state because I just got it by just tiling different toric codes in different patches.
So you're saying that there's like a state in the subspace which has low circuit capacity?
There's no state in the subspace that has low circuit
Right, but
complexity.
that's the counterexample for the toric code?
That's right.
There is one.
Yes, yes, yes. Okay, good. All right. And the types of models that we'll be talking about are quantum LDPC codes with 3 conditions. One is strong enough linear co-boundary confinement. I'll tell you what that is. Non-redundant checks and constant code rate. Okay, so I just have one slide on models here. It's great that I now get to give this talk without explaining all the stuff about these models. So I'm going to be thinking about systems that live on expander graphs. Okay, so these are graphs for which the boundaries of any subregion of small enough size is proportional to its bulk. If you define a classical LDPC code on it, LDPC means low density parity check. So every check acts on finitely many qubits or bits, and every bit is part of finitely many checks. So this just corresponds to locality on a graph. So you can have generalized classical models where, for instance, you put bits on all your edges, and you have some small codes that live on the vertices that act on the bits that surround it. So you can think of these as generalized Ising models composed of a bunch of such checks. Here I just made them 4-body checks for fun, but as long as they're finite, that's all that matters. Okay, N, K, and D, number of physical bits, number of logical bits, the code distance. You can take products of these classical codes to build up these high-dimensional expander graphs. This is a local view of this expander graph, thanks to Nico's excellent drawing skills, where you can see that you get lots of these kinds of book-like structures or pages, lots of local plaquettes that you've created by taking products of these. And now you can put down a quantum LDPC code on this geometry, which is like a generalized toric code, where again it has both X-type and Z-type checks, but they all commute with each other. Okay, and good codes have K and D proportional to N, and the discovery of quantum good LDPC codes is a relatively recent development. And in order to get these good codes, you need these types of expander graphs. Okay, so what actually has been appreciated in the literature, so we kind of got very excited when we found this, but then we found a giant literature that actually had been talking about this, is that there is a well-known relationship between classical LDPC codes and classical spin glass order. Okay, so using again a property called linear confinement, which I'll describe, you can talk about the landscape of these classical LDPC codes. So even for this problem, most of the literature that we found was focused on the ground state and the barriers around the ground state, and not really talking about the rest of the manifold, which we can do. Okay, so here you have again exponentially many stable minima, and the number of relevant stable minima grows with temperature. If you take products of these to get quantum LDPC codes, then these give you this new phase that we're talking about, which is topological quantum spin glass order, which has all of the above properties, but also that each minimum is some highly entangled topologically non-trivial state. Okay, so some comments. These models that I'm thinking about, usually when people talk about spin glasses, they have in mind disordered spin systems, but I'm not thinking about models with any disorder whatsoever. I'm thinking about codes. And in particular, you can even get rid of disorder in the geometry of the graph. Okay, so often people define codes in random regular graphs, but actually we can think about very structured codes which live on Cayley graphs of different groups, which are expanding. So there can be no disorder whatsoever. But you can still prove all of these features about spin glasses using this property of expansion. So this adds to the family of known spin glasses, even in the classical literature. And it might furnish some insight into structural glasses, like, and of course, when you think about window glass, you are thinking about glassiness, the glassiness that comes about due to some kind of geometric frustration rather than due to energetic frustrations. And this family of models is much more in that spirit. Okay.
How do you get like a finite graph which doesn't have disorder?
What do you mean by a finite graph?
Or can you explain how the Cayley graph construction gives you a finite?
So you can't hit every n, every system size, but there are families of graphs which locally look the same, but where your n will jump from 533 to 2000 to something, but there's a whole sequence, so you can talk about an n to infinity limit, while the local view of the graph and the code remains the same.
Okay, I'll ask you.
Well, ask Nico how to do that. But okay, all right. The other point I want to emphasize is that this method of analysis is rigorous. It relies on properties from codes rather than these notions of replica symmetry breaking and so on. So at least to me, it's much more transparent than what is meant by spin glass order as compared to thinking about it in terms of replica symmetry breaking, because I'm just going to be talking about the structures of Gibbs states and equilibrium states. While everything that I'm going to be talking about is in the context of expander graphs, which have been useful in the analysis of many stat-mech problems, like mean field theory, study of classical spin glasses, we do hope that much or some of the phenomenology will persist in large enough spatial dimensions or for large enough times in low enough dimensions, and we're exploring some directions along these lines. Okay, for those who care about experiments, these types of non-local geometries are increasingly more accessible. So we want to start thinking about physics in these types of non-local settings. And actually, we wrote a recent paper together with Nick and Yaodong, who were in the audience. And there was a parallel paper by Andy Lucas's group where we talked about if you have phases, like if you start with some stabilizer code or a zero correlation length fixed point in this kind of expander geometry, and now you perturb the Hamiltonian, the types of stability arguments that we rely on for local Euclidean space, does the gap remain open? Are your ground states kind of look locally similar in some way? You can actually extend those theorems even on these kinds of expander graphs. Okay. As codes, as I said, these models have this exponentially large ground state degeneracy or an extensive ground state entropy. These exponentially large ground states are related by symmetries. If you're talking about topological, these are often higher form symmetries. But already from a physics perspective, having a finite ground state or an extensive ground state entropy is quite unusual. And now we're also saying, that was the point I just made, that if you perturb these models, you can actually preserve this kind of extensive ground state entropy. So usually we have various fine-tuned cases where you can get extensive ground state entropy, but then you worry about third law, and you say, okay, if I perturb it, then that gets lifted. But in this case, actually, it can remain stable. Okay, and then there's a puzzle about these models, which for the quantum context was very nicely kind of put forward in this recent paper by Andy Lucas's group, which is that a lot of these models are known to have these types of codes that I'm talking about. They are known to have robust passive memory with local decoders. These decoders often they're not exactly that, but morally they're very similar to something like zero temperature Glauber dynamics. Okay, but you can look at these models, and in many cases, each check in the model is completely independent from every other check. So you can excite checks independently of all others. So it just looks like decoupled decoupled spins when viewed in the check basis. So the partition function is completely trivial or analytic. It's just the partition function of a paramagnet, okay, at all temperatures. But nevertheless, you can have this type of passive decoding. So the question raised in this paper, and which had already been appreciated in the classical literature for a while, is that even though the partition function looks analytic, which you may think of as thermodynamic triviality, you can get this kind of passive decoding. And what I want to kind of emphasize is that you can have thermodynamic non-triviality in a very sharp way, even as the partition function looks trivial. Okay, so the partition function isn't the only measure of whether something is thermodynamically trivial or non-trivial, and I'll kind of emphasize how you can quantify thermodynamic non-triviality even with a trivial partition function. Yeah.
Maybe you already said it and I missed it. Do these models do they provably have robust passive memory, or is it based on numerics?
I think that these are proofs. Like for the classical one, I think it's proved in Spielman, and for the quantum one, Nico, I think you can comment. I think they are proved too. Yeah, that's right. Okay, so the broader kind of question motivating all of this, we're not kind of finding a memory in a model that wasn't known to have a memory. We're taking these LDPC codes for which it was already known that you have these memories and you have these features, but we're trying to understand it from a physics perspective. Okay, what's the physical feature? Like, if someone tells me the 4D toric code has a memory, as a physicist, I'll say yes, because it has thermally stable topological order. But when someone tells me these LDPC codes have a memory, what should I say as a physicist? And well, now what I should say as a physicist is that these have topological quantum spin glass order, and that's the reason they have a memory. Okay, so that's kind of the broader kind of theme that's motivating this analysis. Okay, so now to delve in, the plan is that I'll tell you about a quantum bottleneck theorem, and this is what we use to define these Gibbs state components, which are these approximate steady states, in a concrete way, and how this helps you also kind of say some more general statements about formulating finite temperature ordered phases of matter. I then want to derive spin glass order from linear confinement, where I'll use this property of code expansion and some structure of energy barriers to define bottleneck subspaces and then apply this theorem. And then I can ask, how does the counting of the number of components behave? Are there components at finite energy density? And finally, I'll talk about the nature of the Gibbs states themselves. Okay? Good. So let's go back to how we talk about distinct Gibbs state components, okay, and let's just talk about classical physics for a moment. So again, intuitively, if I'm saying the 2D Ising model has a non-trivial finite temperature ordered phase, what this really means is that the Gibbs state of the 2D Ising model ceases to be unique in the thermodynamic limit. Okay, this is usually what I mean by spontaneous symmetry breaking, that you have multiple equilibrium states in the thermodynamic limit, and those are related by the action of a symmetry. Okay. But if I look at the Gibbs state, which is e to the minus beta h, of course, this doesn't break any symmetries. This inherits all the symmetries of the Hamiltonian, and this seems to be a unique symmetric state. Okay, this is the global Gibbs state. So what do we concretely mean when we say that the Gibbs state has many components, like this row up and this row down? Okay, and this is a question with a very, very long and rich mathematical literature. As physicists, some of the things that we learn how to do in grade school or in the first StatMech class is that, okay, if you want to define spontaneous symmetry breaking, you should do various things, like, for instance, maybe add a small boundary field and then look at the state that you get deep in the bulk of the system as you take the system size bigger and bigger, and ask, does the state in the bulk care about what your boundary conditions are doing? If it does, then that's evidence of some kind of long-range order, and that you would have different Gibbs states. Okay, so to select out these two different states, you might put in polarized up boundary conditions or polarized down boundary conditions. Another thing people do is to add some infinitesimal symmetry breaking field, take the system size to infinity, and then take the field to 0, and then ask, did the Gibbs state that I prepared in the presence of that tiny field, does it care about whether the field was pointing up or down? Okay, so these are kind of the poor man's kind of versions of what physicists do. There's also some mathematical formalism which directly works in the thermodynamic limit for defining these different Gibbs states. Okay. But in this talk, I want to take a dynamical perspective on how to define these different Gibbs states. This type of perspective has been quite useful in thinking about spin glasses, for instance. And this perspective will kind of couple dynamics and thermodynamics in a way that makes it very natural when we're thinking about memories. Okay, so in this dynamical perspective, we have in mind some system again, and now it's coupled to some bath, which is modeled by some Lindbladian L. The details of this Lindbladian won't be important. You should just think of it as some kind of local detailed balance obeying dynamics for now. Okay? And now the question is, can this Lindbladian have multiple steady states? Okay? And I want it to have multiple steady states, again, in the limit that the system size is going to infinity. So it might have approximate steady states whose lifetime is, again, exponentially diverging with system size. And that's the relevant degeneracy that I'm talking about. Okay? If you have these multiple stable Gibbs states, then you can use those to encode information. And this kind of generalizes the idea of ground state degeneracy to finite temperatures, okay? Which is a degeneracy of this dynamics. But we want the degeneracy to only depend on the properties of the Hamiltonian and the temperature, and not on the detailed microscopics of the dynamics that we use, okay? Because you want it to be a feature of the system and not of the actual kind of dynamics that you're using to get that. So our result is going to be a sufficient condition for a degeneracy. Okay, again, a degeneracy is this non-trivial phase of any local Lindbladian for which the global Gibbs state is a steady state. Okay? And this provides a very general definition of finite temperature phases, and it works for quantum LDPC codes and perturbed quantum LDPC codes at finite temperatures. Okay? Yeah, and this will also give us a way to it's very easy to talk about energy barriers. It's actually much harder to talk about free energy barriers, because counting the entropy when you're talking about free energy is a much harder thing to do. But this also gives us a way to formalize what we mean by a free energy barrier. Okay, and given this kind of degeneracy, this will also lower the mixing time of any such local Lindbladian that has the global Gibbs state as its steady state. Okay, so I should mention here that for quantum problems, which are kind of not stabilizers or classical in disguise, for quantum problems where you have a Hamiltonian with non-commuting terms, for instance, the existence of such a local Lindbladian that prepares an equilibrium state is itself a very recent result just from the last couple of years. Yeah.
Can we talk about the Lindbladian in the infinite system?
Yeah, because you want your jump operators to still preserve some kind of quasi-locality.
So then the infinite system measures that are preserved by the Lindbladian, are they equivalent to the DLR Gibbs states?
I don't know. I mean, they're all going to be closely related, but I think even for different measures of Gibbs states in classical problems, actually showing strict equivalence, I think, is pretty hard.
Also, in problems such as yours, where one gets more and more almost Gibbs states as you increase system size, can one follow a Gibbs state out, from some starting n out to infinity? Do all Gibbs states that you get in the infinite system, can they be traced back to some nascent Gibbs state that appeared at some...
So because you get more and more, that's a very tricky... So I think some you can do, like if I have the uniform state, I can follow that. Yeah. But because I keep spawning more and more, I'm not completely sure how to do that. I mean, that's a question that we should probably think about first, even for like Fracton models in high enough dimensions, which has some degeneracy that keeps increasing with system size.
But so I guess when you say you can construct a family of almost Gibbs states, it's just that there is some number of Gibbs states, almost Gibbs states, at each system size.
That's right.
You can't link this one at this system size to this one at the previous system size.
No, I think you keep spawning more, but the ones that were pre-spawned, you should be able to link, I think. Because I think locally you're not changing anything as you're growing it, right?
So there's no size chaos in a given...
Okay, so I don't know for sure, but my intuition would say that for a given Gibbs state, there is there would be some Gibbs states that continue, which locally in some ball look the same as they did before, because I'm only growing this. I'm not changing the local code at all as I'm growing it. But then there will be other new Gibbs states that get spawned that you can't trace back. Yeah. Okay. Finally, this will allow us to leverage some results on the structure of steady states to talk about classical and quantum memories. Okay, so bottlenecks in approximate steady states. So there's a well-known bottleneck theorem for classical Markov chains, and the picture for this is that take your configuration space, divide it into two regions, and these regions are separated by some bottleneck. Okay, this bottleneck tells you that if you start in A, the flow of probability that takes you out of A is going to be small in some way. And if that's the case, then under these dynamics, there will be an approximate steady state that's confined to A. Okay? That's the picture. I'm going to make it precise in a second. And a key point here is that you're actually decomposing your steady state according to weights or you're decomposing your configuration space according to weights in the exact steady state, which is the Gibbs state, for instance. Okay, so that's why it only cares about properties of the Hamiltonian and not details about your dynamics, as long as you assert that, okay, in my global steady state, I had a region with high weight, I had another region with high weight, I had a region with low weight, and the local dynamics that I'm going to formulate has to go through this low weight region in order to go from A to C. Okay, that's the only kind of feature that you need about the details of the dynamics. But other than that, this decomposition is done purely using the properties of the Hamiltonian. Okay. Okay. So again, let's come back to the 2D Ising model. And here I know that if I'm below TC and I look at my Gibbs state, okay, the majority of the weight in the Gibbs state is on states. Is peaked on states with zero magnetization density. That's paramagnet, that's entropy dominating. Whereas if I'm below TC, then the bulk of the weight in my Gibbs state is kind of separated into these two blobs, one at positive magnetization and the other at negative magnetization. Okay, so if I just make a heat map of take my Gibbs state below some ordering temperature and ask where does it have high weight, well, it'll have high weight in regions where the magnetization is, say, greater than 0.75 or less than minus 0.75, and these will be surrounded by some low weight regions, which are these bottlenecks, where the magnetization is kind of in this dead zone near zero. Okay? So this defines for you these multiple components of configuration space, omega plus and omega minus. Each of these components has weight less than 1 in the global Gibbs state. In this case, because of Ising symmetry, they have weight 1/2, and they are surrounded by these bottlenecks, which are low weight states. Okay. Now, if I can quantify this, okay, by defining this bottleneck ratio, and the bottleneck ratio is just asking what's the weight in the global Gibbs state in this boundary region relative to the weight in the bulk. Okay. Since the Gibbs state is also e to the minus beta f, where f is the free energy, I can take this equation and rewrite it as e to the minus beta f when restricted, the free energy of this boundary region minus the free energy of the bulk region. Okay? And when I have a bottleneck, I want this ratio to be going to 0 in the system size going to infinity limit, which means that this difference in free energy has to diverge with n in the n goes to infinity limit. So this is quantifying for you, using this kind of perspective very directly, what it means to have a free energy barrier in the system. Okay? And now if I think of some Markov chain which has a steady state which is given by my global Gibbs state, and I hit this, so you can again imagine some kind of spin flip dynamics, and if you start in a mostly up state and you start making local spin flips, you know that you have to go through some region where your magnetization gets very, very close to 0 before you can emerge in some region with mostly negative magnetization. So you know any kind of local spin flip dynamics has to go through these bottlenecks to take you from the up Gibbs state to the down Gibbs state. You can actually quantify that because you can think of, let me start with some Gibbs state which is truncated to omega plus, hit it with the Markov chain, and ask how much did I leave that truncated subset. Okay? And the point is, because of this bottleneck ratio, the leakage out of that subspace is very slow. Okay? So in one application, this is less than this 2 delta, which is this bottleneck ratio, which goes to 0 as n goes to infinity. And what this tells you is that if you take this Gibbs state truncated to this to the subspace, this actually has a diverging lifetime, which is precisely 1 over delta n. And this defines for you what a Gibbs state component is. It's some truncation of your global Gibbs state, which has diverging lifetime and weight less than 1. Okay, so you can already see here that this gives you this Gibbs state is associated with memory under local detailed balance obeying dynamics. Yeah, you had a question?
So in practice, for example, in the Ising model, how do you specify your omega or partial omega?
So you can basically just say something like, exactly where you set the boundary is sort of less important, okay? But you can just say, for instance, that omega plus is all spin configurations such that the total magnetization is greater than 0.75, and then omega minus is this being less than minus 0.75, for instance. Okay, so in this picture that I had here, like this could be used, you just set some cutoff, okay, and this could be used to define your Gibbs state components. Yeah.
Do you need sparsity in order to define this bottleneck theorem, or?
Yes, I need local dynamics in general, because I shouldn't be able to jump from omega plus to omega minus. If I can jump and not have to go through the bottleneck, then the bottleneck doesn't play any role. So the key point is that if you have local dynamics, which has to pass through the bottleneck in order to go from plus to minus, then you get sensitive to the bottleneck, and then you can preserve this memory. Yeah.
In this statement of the theorem, where does the time elapse in the Markov chain enter?
Oh, so you what you're going to do is something like, you want to say that you want to ask, like, how many applications of the channel do you apply, how many times do you apply this channel if you're thinking about it discretely, such that you still remain close to omega plus. So you may want to like preserve some distance, or you might want to say like the distance between the state that you're in and omega plus should be less than epsilon, and you can ask how long does it take for some tolerance epsilon that you can define, and then you can just apply this, and you can show that would take some time, which is.
And one more quick question. So I guess there's some amount of arbitrariness in how you choose the omega i's.
Yeah. So there is, but that'll only change things at it won't. It won't have any big impact, because you're talking about something where the weight was exponentially small anyway. So whether you said that at 0.75 or 0.76 doesn't really matter. Yeah. Okay. So non-trivial phase is then one where there's multiple Gibbs state components obtained by truncating to different bottleneck subsets, and extremal components are those that cannot be further subdivided. Yeah.
So do extremal Gibbs states in your setting
Yeah.
have clustering of correlations?
For the classical problem, yes. Even for classical, all of this is classical right now. Even for classical, from some of the things I've read, like these different ways of defining Gibbs states, like through this or through DLR, they're thought to be closely related, but making it precise, I don't think has been done. That you can that they're okay. So with this, I can now give you a very crisp definition of what it means to have classical spin glass order. Okay, what I said was shattering is that you have exponentially many Gibbs state components. Now we know what these mean, that are not related by symmetry. Each component only has exponentially small weight. So this is different from the Ising model, where there were two components, each with roughly half the weight. And each Gibbs state component has some diverging lifetime. In fact, to call it a Gibbs state component, this is somewhat redundant to say that it needed to have diverging lifetime anyway. Okay, and the incongruence is that most Gibbs state components are only contain finite energy density states. Okay, so they're associated with subspaces at some higher temperature. So now, steady states of local detail balance obeying dynamics, we know that these form a convex set, and the point is that each steady state can be written in this following way, where you take your set of extremal states, okay, and you can start with if you just assign different probability weights to these different extremal states, then this is some classical vector, this probability vector. If you have n extremal states, okay, this vector has n components, and the point is that those n components will be preserved under this local detail balance obeying dynamics. Okay, the extremal states are where only one of the p's is 1 and everything else is 0. Okay, but in general, you're preserving this n-dimensional classical probability vector, so you're encoding k equals log log base 2 of n bits, and that's a classical memory that's getting preserved. Yeah, yeah.
Aren't you like missing the region in black?
The region in black basically has negligible weight.
No, but the actual Gibbs state has
Yeah.
a negligible component.
Yes. Yeah.
But that's not captured in this steady state.
So it's only an it's only an approximate steady state, which becomes an exact steady state once I take n to infinity. Yeah. Yeah. Yeah.
The calligraphic n depends on the detailed choice of the bottleneck parameter. Like you mentioned 27 points. Which was more or less clear, because there we go.
Right. Right.
Here we have exponential many.
Right.
I would imagine that it might change that.
So that's right. So it in the cases that I'll discuss, even though you have exponentially many, they're very well separated actually by, because there's a huge configuration space as well. They're very well separated by big barriers and large Hamming distances. But at the edge of a transition, you have many that are starting to merge, and that's when it'll become ill-defined, because your things that go from being almost a memory to not a memory, and at that moment.
So being exponential is pretty robust.
Yes.
The precise exponent is a little bit fuzzy.
That's right. That's right. Yeah. Good. So now we want to do a quantum bottleneck theorem, okay? And this is something that we proved. The point is that the proof of the classical bottleneck theorem writes the probability to kind of leave this region A as a sum over paths, and the quantum generalization, it turned out, was pretty straightforward, but is not immediate, okay? Because you're not just summing probabilities. You now have to care about interference effects and so on. But the setup is now you have some channel, and that channel has some steady state rho. Okay, so this again could be some channel that prepares a Gibbs state for you, but it's quite general. And now you split your Hilbert space into these 4 regions. For technical reasons, we had to divide the bottleneck into 2 bottlenecks, B1 and B2. And the property of this channel is that all the Krauss operators of this channel only have matrix elements between neighboring subspaces. Okay, so that to go from A to C, you have to first go through B1 and then B2 and then C. Okay, so that's how all your quantum trajectories go. And then you can again define a bottleneck ratio, which is quantified by the weight of the steady state in the bottleneck region relative to the weight of the steady state in region A. And this is going to tell you how an application of the channel on A, how much it takes you out of A. And this in turn implies a bound on the mixing time, okay, in terms of this bottleneck ratio, and in terms of this ratio of how much weight there is in A and C relative to B. Okay. One technical comment is there's a square root here, which wasn't there previously. This comes from, now I'm talking about like density matrices with off-diagonal components that live in A and B. So you want the off-diagonal blocks between A and B to also be small. But if you have some kind of more classical-looking dynamics like Clifford, then this reduces to the case with no square root. Okay. All right. So one natural thing in the quantum setting is to consider channels with local Krauss operators. So now instead of thinking about Hilbert space, we're talking about subspace. Instead of talking about configuration space, I'm talking about Hilbert space, and I'm talking about subspaces in Hilbert space. So if I have some subspace V, okay, I can define a neighborhood of V very, very naturally, which is all states are obtained by acting on states in V with some R local operators, and the boundary is the orthogonal component within this neighborhood. Okay, and now if your channel is again K local, then you get this kind of bottleneck result. And once again, you can define a Gibbs state component if this bottleneck ratio is going to, this is what we defined as 10 times delta, if this bottleneck ratio is going to 0, and if the weight in that component is less than 1. Okay? And likewise, you can also, again, there's more subtleties in the quantum problem, but you can also talk about free energy barriers and free energies of different components in this case. Okay. So one last point about this nature of Gibbs states. Somehow I managed to go slowly even here before we move on to the LDPC. Yeah.
What's the relation between the almost Gibbs states in the LDPC code and
Which LDPC code?
the hyperfront, the product.
We'll come to that. Yeah. Okay. So classical versus quantum memory is encoded in the structure of the Gibbs states. Okay. So if you have a classical bit, as I said, you have these two Gibbs states, rho plus and rho minus, and you have p and 1 minus p. That's your classical bit. On the other hand, and these two Gibbs states are orthogonal. Okay. On the other hand, if you have a qubit, and I can think of a logical up state and a logical down state, those are certainly orthogonal subspaces. But now you can also think of a logical plus state and a logical minus state. But those two subspaces are not orthogonal to the logical up and logical down. Okay, so when you have a qubit, there's a different kind of structure that these Gibbs states will take, or these steady states will take. So this is in these math papers from a while ago. And the point is, if you have a quantum memory mu, then if this is your encoded qubit, you have a density matrix which you can think of as your logical qubit, and then that's tensored with some sigma, which you can think of roughly as the syndromes. Okay, so now you can put your system in different logical states, for instance, logical up or logical plus, and that will change this steady state. But that's just each of those choices will be a steady state. Okay, and if I'm thinking about a single qubit, then I'm thinking about a block sphere. As long as I'm on the surface of that block sphere, then I'm a pure state, and if I'm in the interior, then I'm a mixed state. Okay, or a non-extremal state. But this is the structure of every possible steady state of something that encodes the quantum memory. If I have more than one bit, then again I have this 2 to the k dimensional vector for the classical problem. But for the quantum problem, I have a 2 to the k by 2 to the k dimensional density matrix, which encodes the state of the encoded information. So which steady state I'm talking about is dependent on what information I'm trying to preserve, whereas the rest of it doesn't care about alpha. Okay. All right, and then I already kind of mentioned this. When I talk about short versus long-range entanglement, the point is that short-range entangled states are those that can be prepared via some finite depth circuit or some finite time evolution from some product state. And if you have a mixed state, which is short-range correlated, then that can be written as a convex sum of short-range entangled pure states, whereas long-range entangled mixed states cannot be decomposed in that form. Okay, so that's definitions. So now I've kind of told you what the quantum bottleneck theorem is, how to define Gibbs state components. Okay, and now what do you want me to do, Nico? I'm basically.
I don't know, like, how long do you think you'll...
Probably 15 minutes.
That's fine.
It's fine? Okay, all right. Okay, so now I want to use this linear confinement to actually derive these for these specific models. Okay, so this is visually a little bit easier. Okay, so I have a classical expander code, and this code is called delta gamma expanding. Actually, I don't know if this is the right language, but this is what I'm going to call it. Okay, so suppose you start with some classical code word x naught. Okay, and you start flipping bits. There's just some classical configuration. As long as the number of bits you flip is less than delta times n, then the energy that you encounter in doing that is lower bounded by some function that grows linearly with the number of bits that you flip. Okay, so this is like a linear energy barrier or linear confinement, and these linear energy barriers around code words persist up to a finite fraction of flipped spins. Okay, and I just want to say that this is really coming from expanders. It's very unusual if you're thinking about finite dimensional systems, because in finite dimensional systems, if I have a 2D Ising magnet, I can flip half the spins and I only pay a boundary cost, which is less than the bulk. Okay, so I have this linear energy barrier, and the intuitive picture for where this comes from is again because of this expander structure. Suppose you have the all zero state, which is a code word. Okay, and you have these local codes which require you to flip some number of bits to be happy. So now if I flip one bit, I make two local codes unhappy, and now I need to flip more I need to flip more than just one. Okay, that's a feature of this local code to make it happy again, which spreads the pain, and then I keep spreading the pain. Okay, and I have to go to some order n number of flips before these defects can start recombining, and my code can become happy again. So that's why I get this barrier, because I keep spawning more and more defects as I flip spins. But now, I was talking to you about bottlenecks and free energy barriers. But if you have a linear energy barrier, that's the easiest setting. That's the only setting in which a linear free energy barrier is basically immediate, okay? Because you know that that F is E minus Ts. If energy is proportional to n and is extensive, well, the entropy can be no bigger than something proportional to n. So as long as I make my temperature small enough, I have an extensive free energy barrier. Okay, so that's the intuitive picture. In terms of these bottlenecks, what you can do is you can define a configuration which is some Hamming ball of size alpha n, starting from your ground state. And then the boundary of that is things which are some distance epsilon n from that Hamming ball. Okay, and then you again look at the difference in the weight in the Gibbs state between the boundary and the configuration. And the point is that everything that's here in this boundary region just costs extensively more energy. Okay, so because it costs extensively more energy, even after taking this entropic consideration into account, you can show that as long as your temperature is low enough, there's an exponential free energy barrier here, and the lifetime of this bottleneck set is exponential in system size. So using this, you can define at least 2 to the k Gibbs states around these different code words. But you can ask, what are there others at finite energy densities not related by symmetries? And again, it turns out there's a very, very simple argument. It's just an application of the triangle inequality. It's 3 lines of algebra. Let me not do that in the interest of time, but this is a picture, which is now I have some state x, okay, which is at a low enough energy density. And the point is that as long as you have 2 states which are both at low enough energy density, so some energy density less than some order 1 factor here, and they're sufficiently far apart in distance, you can show that these are again going to be separated by extensive energy barriers. Okay? And again, when I have an extensive energy barrier, I have an extensive free energy barrier, so I can host a Gibbs state here. But the size of this barrier is, of course, reduced relative to the size of the barrier around the Gibbs state. So there's a sense in which the finite temperature states are less stable. Okay? This is very, very simple, but I just want to emphasize here that, again, in the context of classical spin glasses, saying concrete things about energy barriers and for finite energy density states using these replica methods, exactly these LDPC codes have been analyzed using replica methods. And you can do it and derive something called the complexity function, but that calculation is so untransparent that by the time it's done, you get some function, but you have no idea where it came from. Whereas this is just like it's 5 lines of algebra, and you get a barrier, and you get a free energy barrier, and you get a Gibbs state. Okay, so it's very powerful. All right. So now you want to do some kind of counting about how many relevant Gibbs states are contributing at any given temperature. Okay, the point is, as you increase temperature, there's of course more and more configurations that you have access to, but those Gibbs states are less and less stable. So there's some competition there. You can do that counting. It's again a pretty simple counting, and what you can show is if your expansion is strong enough, which means that if this parameter, which sets like how steep your energy barrier is strong enough, there's a simple kind of counting argument which you can use to say that each cluster carries a vanishing fraction of the total weight, and you have many clusters at finite energy densities that contribute. Okay, so this is simple, and you can do it. Okay, so we've already done the classical spin glass portion now in 2 slides, whereas if I was giving a talk again on classical spin glasses, I would have spent an hour telling you about replica methods. Okay, so this is why I really like this. Okay, so now let's talk about quantum LDPC codes in topological spin glass order. So as I mentioned, in a quantum code, you have the bit flip part and the phase flip part. You have 2 classical codes, HX and HZ. You combine 2 classical codes to get this quantum code. There are these things called balanced product codes, which Nico invented, where you can again take these symmetric expanders based on Cayley graphs. If you combine them, you get this type of quantum code, and this can give you these good quantum LDPC codes. these have linear energy barriers. Okay, so these have d proportional to n, and they have linear energy barriers. So all of the analysis that I went through for the classical case actually carries over for this case very naturally. The one catch is that we cannot prove, we strongly believe this, and numerics kind of confirm it, but we cannot prove that these kinds of very symmetric input codes have no redundancies, which is a thing that we need. And we also can't prove that this gamma parameter is large enough. There are bounds on gamma, but they're very weak. Okay, but this is just a statement not about we don't believe this exists, but just a belief on what's proven in known models. But then we did actual numerics on these very large balanced product codes, and we did find data that's very consistent with this picture of glasses. So what I'm drawing here for you is a landscape where you have a single logical sector, and you have many valleys, many configurations surrounded by bottlenecks, and this is within one sector, and then it kind of repeats in every logical sector. The consequence of that is that if you start in something like a code word, and you start doing some kind of, this is just stabilizers, I'm just doing classical dynamics, you start doing some spin fluid dynamics, you actually stay in that up to some temperature, which is like a memory temperature, which is what we call a memory time, before you merge with the equilibrium state. Okay. On the other hand, if you do some cooling dynamics where you cool from high temperature, well then you get stuck in one of these highly excited wells. You don't really notice this temperature at all. You actually keep going, you get stuck, and then there's some glass transition temperature, which is a lower temperature than this heating temperature. Okay, so in terms of pictures, above this memory temperature, your Gibbs state looks trivial. Between the memory temperature and the glass temperature, you mostly have all of your weight in the Gibbs state in one giant blob, but then you have very vanishingly few states clustered around these ground states, which are stable, but you never find them if you're just cooling. On the other hand, below this glass temperature, all of these different minima become stable, and then you start cooling and you fall out of equilibrium, and then you hang out somewhere there. Yeah.
The previous slide, what was the definition for gamma again?
The gamma was the slope of the linear barrier.
Oh, I see.
Yeah. Yep. Okay. So this is great. It really looks like it works, but we would like to. I said in my thing that I had a theorem that I proved that there were these topological spin glasses, and actually, well, you can prove them using in hypergraph product codes. Okay, so in hypergraph product codes, you can take hypergraph product codes of what are called Gallagher codes or good classical codes. In those cases, you can directly say there are no redundancies. You can make this gamma parameter for the classical code as strong as you want, and that the quantum code inherits that. So what happens is now I have eigenstates, which in stabilizer language can be written as acting with Pauli X or Z operators on some ground state. Okay, and now once again you get a linear energy barrier, but now you talk not just about Hamming weight, but you talk about some reduced norm, because you act with some Pauli operator and you get a syndrome somewhere, but there's many different choices of Pauli operators that can give you the same syndrome. So we kind of want the minimal choice. That's what this symbol here means. And with hypergraph product codes, like in the toric code, the code distance that you get is actually only root n. Okay, and the barriers that you get likewise only extend to some delta n, which for hypergraph product is root n. So it is a linear barrier, but it doesn't extend all the way to some extensive number of Hamming bit flips. I should say here that this root n barrier is qualitatively different from that of the 2D Ising model, because in the 2D Ising model you have an actual square root barrier extending out to extensive Hamming distance, whereas here you have a linear barrier out to distance root n. So now this complicates some of the analysis that I went through earlier, because earlier I said, like, look, I have a code word, I define a Hamming ball of some size alpha n about that, and then I'm done. Okay, I have a linear energy barrier, I have a linear free energy barrier. Now if I define a Hamming ball of size alpha n, I'm in trouble because this barrier only extends to root n. Okay, so that doesn't actually cover it. So I need a different way of defining bottleneck sets, which actually take into account all typical thermal fluctuations, but still can deal with this, okay? And here I'm saved by the fact that visually, just think about what a low temperature state looks like, right? A low temperature state, we can prove all of this, but a low temperature state, you know, you're flipping some spins, but you're flipping them with very low probability. So if you look at where your syndromes live, they actually form very small clusters which are non-percolating. The typical size of the largest cluster that you have is actually only log n, okay? Because you can think of it as like, is a check excited or not with some probability p independently? So the chance to excite some connected blob of size L is like p to the L. So the largest connected blob in a system of size n is roughly log n. So your typical syndrome pattern, starting from some reference configuration, which is at low enough temperature, actually, that's in red, that actually looks like lots of disconnected patches. And now you add to it typical thermal fluctuations about that, which are again going to be bit flips which are made with small enough probability that they're non-percolating. Okay, so then there can be some cancellations that happen in small places, but each of these patches is very small. So I can independently apply the linear barrier to these patches, because these patches are only log n, and my linear barrier extends out to square root of n. Okay, so typical thermal fluctuations flip an extensive number of spins, but do so in a way that the spins are all in disconnected patches, and that's why typically I have an extensive barrier when I consider these things. Okay, so in particular, what you can do is you can show that up to this delta of n, you can actually apply linear confinement separately, and you get this kind of energy barrier even about finite energy density states. Okay, this delta of n is still going to be something like square root of n, but then I define my bottleneck subset in a different way. I say that things in the bottleneck are configurations which contain some large, almost connected set of size delta of n. Okay, yeah, I have 2 slides left. Okay, so basically you're saying that inside my typical region, I have all of these, I have everything, okay, which are all my typical thermal fluctuations, whereas the bottleneck set is one where my fluctuations form some large blob of size delta of n, which is like square root of n. And this is very unusual, okay? And when this large blob exists, the energy of that large blob is greater than the energy of the things without that large blob by an amount that scales with the size of the blob. So then you get this extensive energy barrier. The number of ways to place that blob such that if you remove it, you get the same kind of state inside this also gives you some entropic counting that you need to do, but you can do it, and you find that you can define these bottleneck sets in this way, and you actually get this lifetime, which is now going like this bottleneck goes as e to the minus order delta of n. So then you get a lifetime, which is like e to the delta of n, which is e to the square root of n. So if you didn't follow all of that, the upshot is just even without an extensive energy barrier, as long as you keep in mind what typical thermal fluctuations look like, and you choose your bottleneck set to be things with a very large connected kind of error, which is not something that happens with typical thermal fluctuations, you can define this kind of bottleneck, and then you can show that each of these highly excited states are also stable. Okay, so for these quantum codes, we've now shown these features of it, which is the shattering and incongruence, even for these hypergraph product codes which don't have an extensive barrier. And in fact, this argument is general enough that as long as your barrier extends to any delta of n which is greater than logarithmic, you're okay. All right. To show that they're topological, this is only one slide. All you're doing is you can't use all the different wells all together because these are distinguished by energy. Energies, yeah.
I haven't followed everything, but maybe just to make sure.
Yeah. Mm-hmm.
Yeah. So why do you say that typical thermal fluctuations are size log L? Necessarily? Because we're talking about thermal fluctuations, not IID noise. So thermal fluctuations are weighted by Boltzmann weights.
Exactly. So just think of it as
no energy penalty for being far apart. So
exactly, but think of it as you have checks, and you can independently excite checks because the checks are all none of the checks are talking to each other. So you can independently excite each check or not with probability p, which is given by the Boltzmann weight. Okay, and now you have some graph of checks where you have like checks and they're kind of connected if they share a bit. But for each check, you're independently going and saying like, are you excited or not? Like if you sample from the Gibbs distribution, you're just sampling in that way. And now you can ask, then it really does look like IID because my checks are independent. And then you can ask what's the largest kind of connected component. And then you get this kind of log n behavior. And as long as the number of relations between your checks is small enough, you can do this. But this is where this lack of redundancies kind of entered our argument. Okay, so now, unlike the classical case where I could use all of my wells all together to define a classical code with a very large code rate, now I can't encode quantum information that's shared between this well and this other well because these two are distinguished by just making an energy measurement, which is local. Instead, you take a well and you take partners of it in all these symmetry-related subspaces, and you can show with, again, pretty simple algebra that an arbitrary state in this subspace has partner states in these different subspaces related by symmetries, which can be used to define a code. Okay, a code in the sense of nil-Laflamme where it's going to have local indistinguishability. And then we can use a recent result in this paper by Bravi, Lee, and Yoshida, which says that if you have any code with finite rate and distance greater than log n, then this is going to be long-range entangled. So then we can use this to show that any state in one of these subspaces, because it has a partner in these different states, is going to be long-range entangled. So this is this very, very strong form of topological order. For this argument, we needed to use the fact that the code had finite rate, but actually given this picture that I was saying about you have all of these disconnected components, and you can kind of quickly heal them down to this ground state, which is a stabilizer state, which you know is long-range entangled. My hope is that you can actually use some argument which is just you have fast dynamics that takes you from any state here to some highly entangled state, which took much longer to prepare, and so any state here must be also long-range entangled. That might connect to some stuff that Thiago will talk about fast mixing within a given well or a given logical sector. Okay, good. So this is why this is like what we call like a mixed quantum classical memory, because you have some classical information which is telling you which well are you picking, and then you have a quantum memory that's kind of encoded across those wells. So this is the summary. You have these different components of shattering, incongruence, topological order, emergent memories, and the kind of bigger picture is that this bottleneck theorem connects these static and dynamical perspectives. The nature of memory is characterized by the structure of Gibbs states. This allows us to analyze new families of spin glasses and helps kind of give a physical perspective to why these LDPC codes have memory. But then in general, it would be interesting to prove these types of bottlenecks in more models of interest. For instance, I don't think this has been done even for the 4D toric code, which we really expect is a quantum memory. Or none of this relied on it, on having to do detailed balance obeying dynamics. So for a lot of these local kind of active models of error correction with cellular automata, it would be nice, like if there's a candidate for some cellular automata that should be stable, then can we prove a bottleneck for that cellular automata? Okay, thank you.
Let's thank Vedika.
Yeah.
Other questions? Urgent questions?
Yes, Kevin. Do you need the high rate in to use the Bravi?
I did. For the Bravi argument, I needed the high rate, but from a physical argument, I don't think I need the high rate.
I think like Anurag in like the predecessor to the NLTS, the like circular bounds for code Hamiltonians, they have a version which does not require high rate. Maybe that could be useful.
So, what do you mean?
Like they have a statement that says like either the ground state or some version of it, like approximate ground state, has a like circuit complexity which is super constant. So long as the distance is sufficiently large, maybe that could be useful for long range entanglement. I haven't seen it in a while though. Maybe.
Were you on this paper, Nico?
No.
Oh, okay.
I think I'm not going to check it.
Yeah, just on our
I see.
Is your mixing time lower bound time?
No, I don't think so. Well, I don't know. We didn't try to make it tight. And that square root was just like a very, it was just like, yeah, very casual. Yeah.
Have you applied to in a specific system and got any
No. I mean, like actual numerically compared to numerics, or
like compared to like upper bounds?
so I mean, you can get the right scaling. Like we applied it to good LDPC codes with these linear barriers, and we argued also for stability, right? Like if I'm talking about these phases, I also want to say that it's stable. So I wanted to say that the bottlenecks are stable and Gibbs states are stable. So we got the right scaling for those, but I don't know about prefactors of those scales. Yeah.
I'm not sure I can pass this coherently. It's confusion of mine. But, so the way I understood a bottleneck is that we're trying to move from one of these excited states to another. We have to sort of pass through this region. So I'm trying to get a picture of this. And I think I understood that at some point when you were dealing with the square root n thing, you said, well, there are these. Yeah, so I'm trying to understand. I don't understand what. I don't understand why it has to pass through.
Yeah. Good. So the point is, I have a given logical sector. Okay, and I have these barriers. Okay, I have some state here that I'm talking about, and the point is that the barrier extends out to some delta of n. Okay, and to go from some state here to another state in this other logical sector, I also have to apply a logical, and the logical has to have some connected component, which is of size at least like this max con that we're talking about. This max con of this logical is again, let's say like sim delta of n. Okay, so if I start from some state and I want to ask about leaving this subspace here, the way I care about leaving it requires me to not just flip delta of n spins, but to actually make a big connected component of delta of n spins that takes me from kind of one logical sector to another. So what I'm saying here is that I'm going to allow for lots of small thermal fluctuations, but I'm not going to allow for these big blobs. But I do need to go through a configuration with this big blob to go from one logical state to another, to go from one state to the state in another logical sector.
Sorry, in your box?
Yeah.
Sorry, where is this big blob sitting? Is that one component of your big blob? Or is that the whole thing?
No. So this is the landscape in say this is the landscape say around the logical 0 state. This is the landscape around the logical 1 state, which I had to act with the logical operator. It's a copy, but I had to act with the logical operator to go from 0 to 1. And this logical operator, you can show has a you can think of building up the logical in kind of big connected pieces. And this has to have a size which is order delta n. So you have to, in order to go from this to this, you actually have to make a large connected fluctuation of size at least delta n, or operator of size at least delta n. And that's very atypical from the perspective of the types of things that thermal fluctuations generate.
Any more questions?
Yes. In one of these papers on this, you talked about like applications to machine learning, and I was just wondering if you had anything in mind.
I don't know. That was when we were trying to get into some fancy journal, but okay. No, it was just. I don't know. Okay, so it's more philosophical, which is like, if you have a classical spin glass landscape, there are of course a lot of these connections from classical spin glass order to things like Hopfield memories, right? And there the point is like, if you have some configuration which is a bit string, which is at the bottom of one of these wells, the training is just like, how do you make this bit string resemble something like a cat, right? That's the training part. But if you don't care that it's a cat, all classical data is basically bit strings. So if you have something at the bottom of this well, and now you corrupt it, like cut the ears of the cat off, chop off half the cat, you can still recover it, right? You can still recognize it's a cat. And that's this kind of recovery process. So now we have the same kind of quantum structure, right? But the states that live here are locally indistinguishable, and they're these highly entangled states. So now it's like, I feel like that should be useful for something like a quantum neural network of some kind, but I don't know what I should be representing. Like everything that we're familiar with, whether it's text or pictures or everything in the classical world can be represented as a bit string. What should I represent using these entangled states? Like what should that? What kind of quantum data can that represent? That's the kind of question.
Yeah. Thanks.
Yeah. Okay, let's take the other questions offline. Let's thank Vedika again for the very nice talk. Maybe we push the next talk a bit later, so maybe let's kind of reconvene at 2:15. Is that okay? Do we have an hour for that? It's not